If you look around, chances are that there is an electrical device nearby, a mobile phone, a computer, a television, something that uses electrical energy to operate. The energy needed to run a mobile phone, for instance, comes from batteries. The transfer of energy takes place via an electric circuit in which the energy source, the battery pack, and the energy-consuming device, the mobile phone, are connected by conducting wires through which electrical charges move. Within a battery, a chemical reaction occurs that transfers electrons from one terminal, leaving it positively charged, to another terminal, leaving it negatively charged. Here we show the two terminals of a car battery and a flashlight battery. The symbol shown here represents a battery or other energy source in circuit drawings. Because of the positive and negative charges on the battery terminals, an electric potential difference exists between them. The maximum potential difference is called the electromotive force, or EMF, of the battery, for which the symbol E is used. The unit for EMF is the volt, which is also joules per coulomb. In a typical car battery, the chemical reaction maintains the potential of the positive terminal at a maximum of 12 volts higher than the potential of the negative terminal, so the EMF equals 12 volts. Thus, 1 coulomb of charge emerging from the battery and entering a circuit has at most 12 joules of energy. In a typical flashlight battery, the EMF is 1.5 volts. In reality, the potential difference between the terminals of a battery is somewhat less than the maximum value indicated by the EMF, for reasons that will be discussed in a later section. In a circuit, the battery creates an electric field within and parallel to the wire, directed from the positive toward the negative terminal. The electric field exerts a force on the free electrons in the wire, and they respond by moving. We can imagine the charges moving inside a wire, crossing an imaginary surface that is perpendicular to their motion. This flow of charge is known as an electric current. The electric current I is defined as the amount of charge per unit time that crosses the imaginary surface, in much of the same sense that a river current is the amount of water per unit time that is flowing through a certain area. If the rate is constant, we can say that the electric current I is the amount of charge per unit time that passes through an imaginary surface that is perpendicular to the motion of the charges, or I equals delta Q divided by delta T. Today, it is known that it is the electrons that flow in metal wires. Here we show the negative electrons emerging from the negative terminal of the battery and moving counterclockwise around the circuit toward the positive terminal. It is customary, however, not to use the flow of electrons when discussing circuits. Instead, a so-called conventional current is used for reasons that date to the time when it was believed that positive charges moved through metal wires. Conventional current is the hypothetical flow of positive charges that would have the same effect in the circuit as the movement of negative charges that actually does occur. In this device, the negative electrons leave the negative terminal of the battery, pass through the device, and arrive at the positive terminal. The same effect would have been achieved if an equivalent amount of positive charge had left the positive terminal, passed through the device, and arrived at the negative terminal. Therefore, the drawing shows the conventional current originating from the positive terminal and moving clockwise around the circuit. A conventional current of hypothetical positive charges is consistent with our earlier use of a positive test charge for defining electric fields and potentials. The direction of conventional current is always from a point of higher potential toward a point of lower potential, that is, from the positive toward the negative terminal. We always use this symbol I to stand for conventional current. If we ever want to know the direction of electron flow, we know that the electrons always move in a direction opposite to the conventional current. In summary, the maximum potential difference between the terminals of a battery is called the electromotive force, or EMF. The electric current is the amount of charge per unit time that passes through an imaginary surface that is perpendicular to the motion of the charges, or I equals delta Q divided by delta T. Finally, it is electrons that move in circuits. The conventional current moves opposite to electron flow. This conventional current indicates the direction of the hypothetical flow of positive charges rather than the flow of the negatively charged electrons.